Hello everyone, today I'm going to show you and explain to you something funny that I will demonstrate with SolidWorks Flow Simulation, and you may actually have seen it before. And what I'm talking about is aerodynamic cooling, and not the common term aerodynamic cooling, which just refers to essentially wind chill, heat transmission, which is of course improved if air moves faster, but actually air actively being cooled below its original temperature by aerodynamic effects, which is kind of counterintuitive since we usually think of like aerodynamic heating. We know that spacecraft, when they enter the atmosphere at high speeds, they heat up so much that the air turns into plasma. And even jet fighters, they don't get like space flight hot, but they still get like everyday hot. And that's not the engine, of course. That's the engine gets really hot, but the fuselage itself also gets like water boiling hot, not plasma hot, but still it warms up, and that is of course the overall end effect. Aerodynamic forces always mean that energy is input into the air, and that in the long run will lead to the air warming up. But on the short run, you can actually cool air below its original temperature. This is just some random thingy I built for absolutely no other purpose than demonstrating this in flow simulation. This is basically built with the sole purpose to demonstrate this and be easy and quick to compute. Now you may have seen this effect earlier in my simulation of a supersonic rotor fin kind of stalling, where you have these areas above and below the wake of the rotor fin, where the air gets, as you can see here, below its inlet temperature. Like the surrounding temperature I set here is room temperature, that's 290 K, and here it goes down almost to 260 K. And here it's even a bit more extreme. The air is inlet at 290 K again. It quickly heats up to above 300 K, since it's essentially compressed through this tunnel at high speeds. And when it's outlet with a certain turbulence and into an expanding tunnel, it actually cools down below 150K, which is like much less, obviously. And the reason for this is actually quite easy. The air is essentially depressurized. If we set this to show pressure instead of temperature, we see that the whole lower area is blue because the range of the scale isn't quite adapt to this yet. Wait a second. Now we can at least see some contours. The air is rapidly depressurized, obviously, because in this case it's flowing through an expanding tunnel. In this case, because of turbulences around the rotor blade, and because it's essentially guided behind the rotor blade, and thus below and above the wake there is depressurized air from those turbulences. And when you rapidly depressurize air, now according to the ideal gas equation, no, not exactly the ideal gas equation, but thermodynamics related to the ideal gas equation, then you notice that if you just ideally expanded some gas using a piston, it would actually cool down in an inverse proportional fashion, such that if you expand it into like infinity, it would actually reach absolute zero. Now this is of course a rough approximation, and it doesn't really work for such extreme values. Of course, thermodynamics is upheld, and you can't really get back any entropy by this, and you can't really cool the air down too far, but you can actually cool it down below inlet pressure, below inlet temperature, just by expanding it and without actually removing any heat, because roughly speaking, temperature is heat energy by volume. So if you expand air and just leave the heat energy in the air the same, the temperature will actually drop, and if you pressurize it, the temperature will actually rise. You can also notice this if you buy like pressured air cans that you can buy for PC and electronics cleaning. I have a few of those. I used to have a few of those for my PC. They are essentially just pressure cans with nothing but air in them, and you can use them to blow dust away. And the air that comes out of those usually is quite cold, and if they're almost empty, they actually cool down themselves because it's pressured gas and air that is depressurized quickly. And this is, of course, limited, and in the long run, since you transmit energy to the air, and since if you don't have a piston, but if you just let air flow through something or have something move through air like a rotor blade, then in the long run the air will go back to normal pressure again, and all the movement in the air will eventually come out as heat. But in the short run you can actually get pretty cold air within turbulences. Now I hope this was kind of interesting, and thanks for watching.